Hey everyone, here is a video on solving and graphing polynomial equations, and it goes along with your worksheet number 1 that I've already given you, hopefully, ahead of time, and you definitely want to take notes on this video. Follow along with what I'm doing. Write down what I write down, highlight what I highlight. This unit will contain a lot of information, but it's kind of neat how it all ties together, and I promise at the end, if you take the time to learn this, you're going to feel really accomplished. So, let's go ahead and get started. Yes, this is going to be a longer video, but again, stay with me. Maybe get some water, some popcorn, and your thinking cap, because here we go. Remember from solving quadratic equations that the solutions of a quadratic equation could also be called the roots, or the zeros, or the x-intercepts. So solutions, roots, zeros, x-intercepts, all of these terms are interchangeable. They mean the same thing whenever it comes to solving a quadratic equation. This will also be true when we are solving polynomial equations. So if you're looking for, if it says the word zeros, you're also looking at the x-intercept solutions or roots. Any of those words are acceptable. They all mean you're doing the same thing. One method used to solve quadratics was factoring, which will also work for polynomial equations, provided that they are factorable. So let's solve the following polynomial equations by factoring. Remember, when we solve by factoring, the first step is always to set the equation equal to 0. And then remember, we would always check for greatest common factor, difference of perfect squares, but that would just be for quadratics. And then we have options such as slip and slide or factoring by grouping. So let's go ahead and look at this first one. We have x cubed minus 2x squared minus 25x equals negative 50. So let's make this equal to 0. So we have x cubed minus 2x squared minus 25x plus 50 equals 0. And I'm going to use factoring by grouping. So I'm going to group the first two terms together, the second two terms together, and looking at my first group of terms, my greatest common factor is x squared. So I have x squared times x minus 2. When I take out the x squared, I'm left with an x and a negative 2. Now looking at my second group of terms, I've got a minus sign in the front, so I'll take that out and put it in the front. And looking across, I can take a 25 out of both terms, so I take out the negative 25. And when I divide out the negative 25 from each part, I get x minus 2 again. So then looking across the whole thing, I've got a binomial here. Here's my first and then my second term. My greatest common factor between these two things is x minus 2. And when I take out the x minus 2 from each, on the first part I'm just left with the x squared. The second part is the negative 25. But I'm not done here. My x minus 2 still stays in the front, but x squared minus 25 factors into x minus 5 and x plus 5, because that is a difference of two perfect squares. So I take each of these factors, set them equal to 0, and solve for x. So I'll get x equals to 2. Here I'll get x equals 5. And here I'll get x equals negative 5. So these three things right here, 2, 5, and negative 5, all of those are the roots. Oops. Okay. Let's take a look at another example here. You can also check out this exact same example on page 438, example 1b in your textbook. But let's start out the same way. Let's get everything equal to 0. So we have x to the 4th minus 13x squared plus 36 equals 0. I have a trinomial here. So I can actually factor this as the product of two binomials. X to the 4th is the same thing as x squared times x squared. And what multiplies to positive 36 but adds to negative 13? Well, that's negative 4 and negative 9. I kind of knew that I was going to be able to do this because I had an x to the fourth and then an x squared and then an x to the 0. It went down by 2 each time, and so that told me I could factor it like this. So I've got two binomials that are both a difference of perfect squares. So this first term factors into x minus 2 times x plus 2. My second binomial factors into x minus 3 times x plus 3. This is all still equal to 0. So when I set each of my factors equal to 0 and solve for x, on this one I'll get x equals 2. Here I'll get x equals to negative 2. Here I'll get x equals 3. And here I'll end up with x equals negative 3. So this time I had 4 roots. Okay, let's look at one more. Okay, we have 3x to the 5th plus 18x to the 4th plus 27x cubed equals 0. You can also see this is like page 438, example 1a in your textbook. But the first thing that we do is get it equal to 0, but we always check for the greatest common factor first. And here, the greatest common factor is a 3x cubed. When I take out the 3x cubed, I'm left with x squared plus 6x plus 9. Now that is equal to 0. So then this trinomial here factors into what multiplies to 9 but adds to 6. Well, that's 3 and 3. So here I'll again set each of my terms that are equal to 0 and solve for x. So I'll divide by 3. I get x cubed equals 0. And the cube root of 0 is still 0. For this one, I'll take x plus 3 and set it equal to 0, and I'll get x equals negative 3. When I do the same thing for the second one, I'll end up with x equals negative 3 again. So notice I have x equals 0 and x equals negative 3, and that's there twice. So on the first example up here, I had x cubed. My degree for this polynomial was 3 because my highest exponent was 3, and I ended up with 3 roots. On my next one, my polynomial, the degree was 4, and I ended up with 1, 2, 3, 4 roots. On this last one, my degree was 5 because my highest exponent was 5. Glancing down at our answers, though, did we stick with the pattern of our degree matching the number of roots? Well, actually, yes, we did, because notice that we had x cubed equals 0. So really there are 3 solutions represented right there. So there's 1, 2, 3. And then here's the negative 3 once and the negative 3 twice. So we have 3 solutions of 0, and 2 are at negative 3. So there are still 5 solutions for this polynomial, and so the degree does match the number of solutions. So just kind of a recap on what we just said. Notice that the cubic equation has 3 solutions and the quartic equation has 4 solutions, but it appears that the quintic equation only has 2 solutions. If a polynomial equation has a factor that appears more than once, then that factor is called a multiple factor, which then leads to its root being called a multiple root. In the case of the quintic equation above, the root of 0 is a root 3 times because of the factor 3x cubed, and the root of negative 3 is a root 2 times because of the factors x plus 3 times x plus 3, or that's the same thing as x plus 3 squared. When a root occurs more than once in a polynomial, the root is said to have a multiplicity of 2 or 3 or whatever the exponent would be, depending on the number of times that x minus r is a factor of the polynomial. Therefore, in our quintic example above, 0 would have a multiplicity of 3, and negative 3 would have a multiplicity of 2, giving the quintic equation a total of 5 solutions. Here's what we're going to call the fundamental theorem of algebra. Well, it is the fundamental theorem of algebra, and it states that every polynomial function of degree n greater than or equal to 1 has at least one zero, where 0 may be a complex number. A corollary for that would be every polynomial function of degree n greater than or equal to 1 has exactly n zeros, including multiplicities. Since roots or solutions or zeros are also the x-intercepts of the polynomial function, it is helpful to remember when graphing polynomial functions that when a real root has an even multiplicity, for example, 2, 4, 6, even, the graph of the polynomial touches the x-axis at the root but does not cross the x-axis. And when a real root has an odd multiplicity greater than 1, example 3, 5, 7, etc., the graph of the polynomial bends as it crosses the x-axis. So if it is a real root and it has an even multiplicity, it will touch the x-axis, but it won't cross. It'll bounce off of it. But when a real root has an odd multiplicity greater than 1, it will bend as it goes through the x-axis. So let's look at the graph of the quintic equation we were just looking at a moment ago. So you have f of x equals 3x to the 5th plus 18x to the 4th plus 27x cubed. So remember that we had 0 and negative 3 as solutions. So the root negative 3 had a multiplicity of 2. So since the multiplicity of 2 is even, 2 is an even number, that means on the graph it will only touch at that root, so at negative 3, 0. But it won't cross. It will go to negative 3 and it'll bounce right back off of it. It will not go through the x-axis. However, the multiplicity of 3 for the root of 0, 3 is an odd number, so that means the graph will bend as it goes through that root. So notice the graph does not cross the x-axis at negative 3, but touches and goes back down, and that the right arrow is rising, going up, since the leading coefficient of the polynomial is positive. That's an important thing to know. About the right arrow will go up since the leading coefficient of the polynomial is positive. And the left arrow is going down, it's falling, since the degree of the polynomial equation is odd. So the right arrow and left arrow represent what is called the end behavior of a graph. And this is also really important, and we'll summarize what we just said in a table here below. But end behavior is a description of the y values of the function as x values approach positive infinity, which is going to be the right arrow on the graph, and as x approaches negative infinity, which is the left arrow. Okay, so what I want you to do here is to pause this video for just a moment, and I want you to read through this table and see if you notice any patterns. So take a moment and pause it, and then unpause whenever you're done reading. Okay, so let's take a look at this first half of the table, the top part. So we are looking at a leading coefficient that is positive. So this is a positive polynomial. The bottom part is for a negative leading coefficient. So when we have a leading coefficient that is positive, if we have an odd degree, as x is approaching positive infinity, the y values are approaching positive infinity. The right arrow is going up, or it's rising. And as x is approaching negative infinity, the y values are also approaching negative infinity. The left arrow is going to be falling or going down. Think of an easy, basic, odd degree polynomial. And you could get y equals x cubed. So this matches what we're talking about. The leading coefficient is greater than 0. This is a positive x cubed. And we have an odd degree because of that exponent. And remember that the graph of this, y equals x cubed, would look something rough like that. And notice it follows exactly what we're saying. For x approaching positive infinity, the y values are approaching positive infinity. So on this side, as x is going to be slowly getting bigger and bigger, the y values are going to be getting bigger and bigger. And then it says as x approaches negative infinity, the y values approach negative infinity. So on the left side, this will be going down. So the right arrow is going up, left arrow going down. Let's check out if we have a leading coefficient that is positive and it's an even degree. So as x is approaching positive infinity, the y values are approaching positive infinity. The right arrow is going up. And as x approaches negative infinity, the y value is still approaching positive infinity. The left arrow is still going up. Think of a really basic example of an even degree polynomial, and you get y equals x squared. And remember, a graph of that, is a parabola. So we have an even degree, and watch that this follows exactly what our graph is doing here. As x approaches positive infinity, the y values are going towards positive infinity. The right arrow is going up. And as x approaches negative infinity, the y values approach positive infinity. The left arrow is also going up. So notice our pattern here. Odd degree means arrows are going in opposite direction. But as long as our leading coefficient is positive, the right arrow goes up. So that's something important for you to notice. That as long as we have a leading coefficient that is positive, the right arrow goes up. All you need to know is that odd means that the arrows are opposite. And even degree means we have the same direction for the arrows. That doesn't flow as well, but the O's match. So if it's odd degree, opposite direction of the arrows, and no matter what, if the leading coefficient is positive, the right arrow will go up. And if it's odd, the left will go down. If it's even, the arrows will match. Let's look at if the leading coefficient is negative. So if we have a leading coefficient that is negative and we have an odd degree, it still is true that if you have an odd degree, you will have the opposite direction for the arrows. Let's look back at our simple example. We just need to change the y equals x cubed to y equals negative x cubed. So that way our leading coefficient is negative. So if we have the graph of y equals negative x cubed, that means we'll take the parent function and flip it over the x-axis. So now it just switches the other direction. And watch what it's saying here. As x is approaching positive infinity, f of x will go down. The y values, the right arrow is going down. And as x approaches negative infinity, the y values are going up. The left arrow is going up. So here, this time, the leading coefficient is negative. So the right arrow will go down, no matter what, if it's even or odd. Okay, and remember, we still have opposite arrows. Let's check out the even degree when the leading coefficient is negative. If we have an even degree, so let's say this time it's y, switch colors here, y equals negative x squared. So that means that parabola would be opening upside down. messy, sorry. Okay, so if the leading coefficient is negative, as seen at the negative x squared, that means the right arrow will go down. And it's an even degree, so that means the left arrow will match it, so it will also go down. So it's true again, even degree has the same direction for the arrows. Okay, feel free to ponder that for a moment, let that sink in, marinate a little bit, so that way you are really understanding what I was saying here. It's not that these are the only examples x cubed and x squared that you'll see, but it doesn't matter how much more complicated it gets. All you need to look at are the leading coefficients, if they're positive or negative, and the exponents if they're odd or even, and you can figure out which direction the arrows will be, the end behavior, based upon these simple examples right here. So it's important to remember these examples right here. You can always refer back to them, and they'll tell you about the end behavior no matter what your polynomial is. Okay, you'll see in your packet of notes there that this funny looking picture here. This is another way to talk about the end behavior, and it relates to limits of a function. So you'll see these arrows all over the place. So looking at quadrants 1 and 4 here, what this is telling us here is that if the right arrow is going up towards positive infinity, that means that your limit of that function is going to be infinity, and that your arrow will end up in quadrant 1. Okay? If it is the right arrow is going down, then the limit of your function as x approaches positive infinity is going to be negative infinity, meaning as x is getting bigger and bigger, the y values are getting smaller and smaller forever. So that limit of that function as x is getting larger is going to be negative infinity. On the other side, quadrants 2 and 3, if your arrow, your left arrow, is going up, that means as x is getting really small, the y values are getting really big, that means that your function will end up in quadrant 2. In other words, your limit for your function as x is getting really, really small is infinity. In other words, as x is getting really, really small, the y values are approaching infinity. They're getting really, really big. So this side is where x is negative, and above is where y is positive. So it's going to be going towards positive infinity as x is getting smaller. As opposed to the opposite, if your left arrow is going down, that means it will end up in quadrant 3. In other words, as x is getting really, really small, the y values will continue getting really, really small as well. So the limit of a function f of x, if your left arrow is going down, is going to be negative infinity as x gets small. Okay, don't let this picture scare you, but it is important for you to see this and just take a moment and kind of look at it and see, okay, am I understanding what this is saying? Feel free to ask me questions whenever I see you in class. Okay, so let's go back and sketch the graphs using x-intercepts, the y-intercept, and the end behavior as guidelines for these first two problems. So these two problems were on the first page. So remember that for f of x, this first one here, we ended up with solutions of -5, +5, and 2. In other words, we had no multiplicity. For any of these roots. Okay, so looking at our degree of this polynomial, we have an odd degree polynomial. Also, we need to know, is this a positive or negative? What is the leading coefficient? The leading coefficient is 1. It's greater than 0. It's a positive number. The leading coefficient is greater than 0. Okay, so we have everything that we need here. Along with, it also said the y-intercept. Remember, the y-intercept always has an x value of 0. So when x is 0 in our function, all that we'd be left with is this constant term. So remember, the last term that has no x in it is the y-intercept. So the y-intercept here being 50 is somewhere way off the graph. I'm just going to put a point up there to say, okay, my y-intercept is somewhere above that graph. Obviously, it's way more than that, but that's okay. Something to kind of aim towards. Okay, we also know our roots here. So we have -5, 5, and 2. I'm going to put those on the graph. These are the x-intercepts. So 1, 2, 3, 4, 5. There's -5. We also have one at 2 and another one at 5. Okay, so those are the roots. Now let's consider the arrows. An odd degree means opposite arrows. Okay, odd degree means opposite arrows. And I can figure out the direction of the right arrow based upon my leading coefficient. Remember, if your leading coefficient is positive, then your right arrow goes up. So let's think of that first. The leading coefficient is positive, that means the right arrow goes up. Does not matter what the degree is. If the leading coefficient is positive, the right arrow goes up. Now, since the degree is odd, that means the left arrow will be opposite and it will go down. Now, we had no multiplicity for these roots. So remember back, it said if you have multiplicities that are even, that means you would bounce off of the x-axis at that root. But if it's odd, then it would bend as it goes through it. But here we have no multiplicity whatsoever. It's just these happened one time. It didn't happen multiple times. So that means it'll just go through it like normal. We don't have to worry about it bending or anything. The rest is just connect the dots. So I go through the x-axis here, go towards my y-intercept. At some point I turn back around. I'll go back down. At some point I'll turn back around and go back to that one. So notice, I didn't bend as I went through these roots, and I connected all the points. Now, where I made the turnarounds does not matter, except for that I connected all of the points. So this isn't necessarily the most accurate. It does say we're just sketching it, so we're not being too picky. What we're looking for is the direction of the arrows, the roots, the y-intercept, and the behavior of the graph as it goes through the roots. Let's look at this other one. So we had x to the fourth minus 13x squared plus 36. So here we had roots of 2, -2, 3, and -3. So again, these do not repeat. There are no multiplicities. My y-intercept again is this last term. That does not have an x with it. Okay, so here, my leading coefficient one x to the fourth. So my leading coefficient is greater than 0. It's positive, okay? And then my degree is even. And I knew that by looking at my highest exponent of x to the fourth, and that's an even number. Okay, so start off, we could put the y-intercept if we want to. Again, it's somewhere way off the graph. I can plot my roots. So I have at -1, 2, 3. I've got one at -2. It's going to be a little crowded here. Got one at 2, and then also again at 3. Okay, my leading coefficient is positive. So that tells me right away, it does not matter what the degree is, but because it is positive, the right arrow will go up. Because my degree is even, the left arrow will match the right arrow, and it will go up as well. I did not have a multiplicity anywhere, so my function will go through those points without bending directly at that point. But otherwise, you just connect the points, and so you get this funny looking W thing. Again, it does not matter where you're turning around down here at the bottom of this function, the bottom of this W that I made. That does not matter. That's not what we're looking for. It is a sketch. We are looking for the arrows, the roots, the y-intercept, and the behavior of the function as it goes through the root. We're almost done, you guys. Stick with me. You're almost there. Okay, so the last part of what we're looking at right here is talking about where I turned around on the graphs above, where I said it doesn't really matter where we're putting it on our graph. And this is why. Let's read this paragraph here. Where the graph changes from increasing to decreasing or decreasing to increasing, in other words, it changes directions, corresponds to a turning point in the graph. A polynomial of degree n greater than or equal to 1 can have at most n minus 1 turns. So whatever the degree is, it will have 1 less turns at most. So if we had a degree 4, it could have at most 3 turns. If we had a degree 5, it could have at most 4 turns. Okay, using n behavior along with possible number of turning points, one can conclude that an odd degree polynomial will have either no turns or an even number of turns, so that the n behaviors are opposite of each other. So we're wanting to maintain that an odd degree has opposite arrows. And an even degree polynomial will have an odd number of turns, so that the n behaviors will be the same. And you can look at the above examples for that. A turning point in a graph is called the local maximum or a local minimum. So turning points are maximums or minimums depending on which direction they open. Of course, if it opens down, it's a maximum. If it opens up, it's a minimum, just like we looked at quadratics. Graphing calculators can be used to determine the values of local maximum and local minimum when necessary, but as far as our sketches go, we will not be particularly picky about those points. Just know that they exist, what they're called, and we would find them on the calculator. So just one more clarification here. Notice we have opposite arrows, so it's an odd degree. So it could be a degree of 3. So notice we only turn 2 times. We turned twice, so that way the arrows would remain in an opposite direction. If we had turned 1 more time, the arrow would have gone in the same direction. But this is an odd degree, so opposite arrows. Okay, you have made it through the first worksheet. They won't all be this bad because this is like an introductory lesson. Hopefully this made sense. Go back, rewatch this if you have time, or if you have questions on a particular part, go back and rewatch it. This is important for you to get this from the beginning of this unit. Do not take me lightly here. Okay, write down any questions you have, make notes on your paper, ask me when you get into class tomorrow. And I will see you then. Bye.